In this video, we are going to prove why Edmonds Karp's algorithm runs in time, big O of V times E squared. Recall that Edmonds Karp's algorithm always finds the shortest augmenting path from a residual network. So there may be more than one path on the residual network. Edmonds Karp always finds the shortest one. Okay, so then we can show that the running time of Edmonds Karp is big O of V times E squared, which is independent of the value of the maximum flow. Hence, it is an improvement over forward-focusing algorithm. Remember, forward-focusing algorithm runs in time of big O of it's a big O of the value of the maximum flow times V plus E squared. Okay, so that it depends on the value of the flow. And Edmonds Karp is independent of the value of the flow. Okay. So first, let's prove this lemma for any node V, which is intermediate node from S to T. So say this is a path from S to T. So this is SST. So for any node on this path, intermediate node, which is not S or T, we will have that, let's say this is a F with a flow F, and then F prime is based on is afterwards. Okay, so this is F prime is the flow after F, and for any V here, for the same node V, and the distance of the shortest path from S to V, okay, will always be less than or equal to the distance of the length of the shortest distance of S to V from F prime. So usually it could mean either on a different path or it's so it will be if it's V on F and F prime, right? So that's going to happen. Okay, so that's what we're going to prove. So we prove it by contradiction. So that means that there exists V that violates this condition. So that means for some F and F prime is after F, that we have this situation. So that's what this means. Since there is such V, we can always pick the V that is closest to S. Okay, so that's what this bullet says. So V is the closest node to S on the shortest path P, okay, with this conditions. That's true. So this is by assuming that lemma is not true. The lemma is not true. So on this path P, on this path P, so we have a node. So before V, we have a node U. Okay, so because V is an intermediate node, so U could be S, right? But there must be some node before U such that U to V is an edge on EF prime. Okay, for this case, then we have delta F prime SU would be delta F prime SV plus 1 because there is an extra edge. And also, this U is closer than V to S. Okay, so that means we must have this. Okay, so we must have this. So now let's move on to the next slide. So now we're going to show, we're going to prove that UV is, so we're going to say UV, so this edge is not in EF. Okay, so we prove it by contradiction. So that means if it is in EF, okay, so that means if, so this is an edge, if U, V, this edge is in EF, okay, so that means it has a flow, right? So the flow if it's in EF, that means that the distance on F, the distance, so this is S here. So this is S. Can I write it? I don't know. Let's do it again. Okay, so maybe change the place. So this is E, V. So this is U, S here. To here. U, V, S. Okay, so so on this path, then we have the distance from S to V on F will be less than or equal to distance from S to U and plus this edge. Okay, so that because it is in EF. Okay, so that's what we have, plus 1, because adding this edge. And then by assumption that delta FSU is less than or equal to delta F prime SU, so that's what we have, this inequality, and this is actually is equal to delta F prime SV. So this then is a violates, because it violates the assumption that delta FSV is greater than delta F prime SV, right? So that's a violation. So that means that this UV, U arrow V cannot be in EF. So that means because, so this U to V is not in EF. but we know that u to v is in EF prime. So that means from V to U. So there is a flow going through U to F in F prime. So that means that in the residual network from V to U, it must have an augmenting path that's increased. So from V to U, there's something, you added something, so that it's F prime added to it. So that's added to it. So this is the second bullet, right? So the augmentation must increase the flow from V to U. And then you will look at, first we know Edmonds Karp always augments flow along the shortest path. And we know that the U is next to V, is a position node to V. So you may, we want to say where this U. So let's say we have a shortest path S to U in GF. So let's look at this shortest path. I want to know where this V is on this path. Okay, we know that the U to V cannot be on this path. So this cannot be on this path in GF. So then if V is on this path, then V has to be in GF, right? So that's what it is. Okay, if V is not on this path, then it won't be, so it won't change this value from V to U, right? So if V is not on this path, then of course F prime is not going to change that value, the augmentation. So that's not changed, because usually if if V is not on this path, that means V has, right? So you got, let's say this is possible V here, and this particular V is not on the path, so the augmenting path is not on the augmenting path, and hence from hence the augmenting path cannot. So if it's not on it, so the augmenting path and the flow will not affect this edge, right? Because the only thing that's affected is when V is on the path. So when V is on the path, then this has to be true. So that's what we have here, right? So that means on this path, S will go to V and then go to U. So then we can compute the distance from S to V on the delta F SV is equal to delta F SU minus 1, right? But then by assumption, we know delta F SU is less than or equal to delta F prime SU, and delta F prime SU is equal to, earlier we saw that in the previous slide, we know that delta F prime SU is equal to delta F prime S V minus 1. Okay, so that means that it's equal to delta F prime SV minus 2. So that means that delta F SV is greater than delta F prime SV. Okay, and sorry, less than, right? Because this is equal to something minus 2. So that means that you remove minus 2, it is less than. So that means it is less than. It's less than, sorry, let me put it here. It is less than delta F prime S3. But our assumption is this. So that's a violation. So the violation indicates that the lemma is true. All right. So next, we want to show that Edmonds Karp will perform at most an order of V times the E flow augmentation. So that means we want to do some counting here. So we want to do counting. So so when we do counting, we need a handle that we can count. So that handle we use to count, you use to do this counting is something called a critical edge. A critical edge is an edge. So let's say this is U, this is V. So we want to count, say this is on the pass, right? So this is on the pass. This is on the pass, on the pass. So this is a critical edge is when the capacity, the residual capacity of this edge is the smallest of the residual capacities of all the other edges. So which means that, let's say this is F. So when you, so this is from GF. This is on GF. And then you find a F prime, then this edge disappeared. Okay, and then you have the opposite. So now I want to use a critical edge as a handle to count how many times each edge can become critical, because after a while, it may appears again. So then V arrow U appears because it is selected, and then U after that, when this is selected on the pass, then after it's augmented, UV will appear again. So once UV appears, then it could become, at some point, it could become critical, okay? So I want to know how many times it could become critical. So that's the handle we use to do this counting. Okay, so now let's look at this slide. So each edge can become critical at most V over 2 times. So that's what we want to show. So first, let's assume that E is critical for the first time on F. So that means that for this particular GF, E becomes critical. E is UV, okay? So this edge becomes critical, so that means that delta F SV is equal to delta F SU plus 1. That's the first thing. And second thing is that when the flow is augmented, E disappears, okay, from EF. And E could appear again until, okay, so it cannot reappear until after VU appears on the augmenting path. So in other words, until after VU is selected, so that means on the augmenting path. So then we let F prime be the first flow when this happens. So that means that delta F prime SU, okay, is equal to delta. So in other words, when V U appears on an augmenting path. Okay, then in this case, let's say this is on F prime, then delta F prime SU is equal to delta F prime V, then plus one more H. So that's what it is. By assumption, because F prime is after F, so by assumption, I'm sorry, by the lemma we proved earlier, we have this. Now remember this V is intermediate node, okay, for the intermediate edge. Okay, so that's E. Okay. So that's what we have. So delta F prime SV is greater than or equal to delta F SV. Then from here we get, so this is greater than or equal to delta F SV, so that and delta SV is equal to delta SU plus 1. So that's what we have. So that means that, now how do we interpret this result? The result says that for U, which is intermediate node, what we are having here is that the, let's say U here on GF, okay, you have going there, so that's S. And U on F prime, different roots. So the length of this is at least 2 more edges than the length of S to U. Okay, so that means each time you get 2 edges longer. Each time you get 2 edges longer. Now, how many times you can get 2 edges longer? Then you just count a shortest path from S to U. What is the longest possible from S to U? Now, U is intermediate. Now, of course, we know that it would be at most V minus 2 edges. Okay, because it doesn't count T. If it counts T, then it's V minus 1 because you can really, the longest you could have is all the nodes are in it. That's V node. There are V nodes, and then the edges will be V minus 1. Okay, so that's, we were here, right? So then that means that, let's say the total number of times is K times that we can, an edge can become the same edge, right? The same edge UV can become critical. So each time from S to U, the distance is at least 2 more edges, 2 edges longer. So that means that if I have K times, then 2 times K, the total number of edges you have increased. That's 2 times K, then it's at most V minus 2. So that means that K, the times you do is V over 2 minus 1. Okay, so that is the total number of times each edge can become critical, can be critical. So after that, this edge can no longer be on any augmenting paths. So that you have this many edges, so that means altogether, the total number of times augmentation can occur. Augmentation can occur is E times V over 2, right? But it just use a big O. So that's that. And then finding an finding a shortest path from S to T using either breadth first search or depth first search takes big O over E steps. So that means then Edmonds Karp algorithm is a big O of E squared times. Okay, so that is the proof of Edmonds Karp algorithm. It is quite involved. It is a combinatorial proof. It is quite involved, much harder. It's much harder than proving Dijkstra's algorithm. The greedy choice, right? Greedy choice. In Dijkstra's algorithm, finding the shortest augmenting path is also a greedy choice. Okay, so this proof is harder, probably one of the hardest in this course. We are going to see in the rest of it, in the rest of the semester. Okay, so that's the end of this video. In the next video, we are going to show using minimum cuts why this greedy choice works. Okay, so we are going to show why finding a path from S to T from a residual network will give us a maximum flow, right? So that is the problem we need to answer, right? So we're going to do that in the next video.